Hello everyone, my name is Abulfaz Mahmoudpour, and in this video we are going to continue discussion about the solving out the nonlinear Poisson equation using finite difference method. But this time we will use new method for calculation of the discrete form of the Poisson equation. We will see that this method, although helps for increasing the convergence speed, but it has its own disadvantage. So let's see. Okay, this is the general form of Poisson nonlinear Poisson equation that we have discussed in the previous video, and you can find the previous video in this link. What we did, we just decomposed the equation into two terms, as you see here. Then we derived the discrete form of this equation, and we saw that discrete form of this equation is following. And by solving of this equation in MATLAB, we got such a behavior for the convergence of the problem. And you see that for some case, when n1 is 1e14, 1e15, 1e16, we have more or less good convergence. But for very large value of n1, we see that we do not have any convergence, and we have very strong oscillation of the solution. Then for solving of this problem, in order to have convergence for all set of parameter, what we did, we just linearized the Poisson equation, and we saw that now the form of the linearized Poisson equation is following. We derived discrete form of this equation, and we ended with such an equation. Then by solving of this equation, we got such a convergence for different value for n1, and you see that by linearization we have convergence for all n1, and the convergence efficiency increased just by linearization. If you compare this orange line with this, you see that here we need about 1000 iteration to have such a convergence, but here the required number to get the convergence is even less than 100. Now in this video we are going to check, can we further improve the convergence of the problem or not. Let's do following. We have again the same problem. This is the linearized form of the Poisson equation, and from finite difference method we know that the discrete form of such equation can be right like following. Okay, what if we just multiply both hand side of this equation with h squared and gather all term with vi here, and we have the right hand side as following. And previous time we just keep this vi at one side of equation, and we gathered all the other terms at the other side of equation, and we call this method one by one calculation. Why? Because we need to first calculate the grid number 1, but we know the value of the grid number 1 from the boundary condition. Then we calculated grid number 2, grid number 3, so on and so forth, and we did it inside the loop. There are another method, and this method is just following. We keep the form of equation like this, and just substitute I with numbers. We substitute I equal to 1, I equal to 2, I equal to 3, I equal to 4, and I equal to 5. You see that by substituting I we have these terms: v1, v2, v3, v2, v3, v4, v3, v4, v5, v4, v5, v6. What we did, just we substitute I with some number, and we assume that here the number of grids is 6. That's why we just strip the I from 2 until 4, and by substituting I from 2 to 4 we will end up with such a system of equation. But you see that we have term v1 and term v6 at the left hand side, but we know the value of v1 and v6 because our problem is a directly boundary problem, and we know the value of the v at the boundaries. Therefore, this v1 and v6 are known, and we send known value to the right hand side of this equation. Doing that, we will end with this with such a system of equation. And if you notice, we can write the matrix form of this equation. And the matrix form of this equation will be following. We have V2, V3, V4, V5. We have some coefficient that all are known because A is some parameter, H is parameter. We know the value of N2 from the first equation. We know the VTH, and all the other term here are just some number. And even in right hand side, all value are known, and this V1 and V6 are known. And if you just multiply this matrix to the D's, you will end up with system of equation. Very simple. For example, at the first equation, you see that the coefficient of V2 is this. 1 multiple to the V2 is the same term. 1 multiple to the V3 is the same term. And at the right hand side, we have this term here and this one here. And same for the rest of the equation. Therefore, it's for deriving of the matrix form of the equation, try to calculate it for a limited number of grids. For example, what I did here, I assume that the number of grids is 6. Therefore, I just substitute I from 2 to 5. By substituting I from 2 to 5, we got all the V1, V2, V3 until V6, right? Then by having this system of equation, you can easily derive the matrix form of this equation. And if you notice, if I just call this matrix with some n, and I call this matrix with some VC, and call this one with right hand side, and this one with right hand side B, that here B stands for the boundary condition. It means that the right hand side due to the boundary condition. Therefore, by having of the matrix M, calculating the inverse of this matrix M and multiplying it to the right hand side matrix, we can easily calculate the unknown variable that is V in our equation. Therefore, using this method, just by matrix form calculation, we can easily calculate the value of the potential at all unknown grid, right? Just with a simple matrix multiplication. And if we do that, we will see that for when N1 is 1E15, we have such convergence for one-by-one calculation. One-by-one calculation, I mean the method that we have used in the previous video. And this is the convergence for the direct calculation or inverse matrix method, or whatever you call. You may call it direct calculation, or you may call it matrix form calculation or inverse matrix calculation. And we will see that by using of this direct calculation, the convergence the convergence speed is slightly increased, as you see in the graph. And just some comparison for different number of grid. See, this one is for one-by-one calculation, right? This graph is for one-by-one calculation. You see that when number of grid is 100, is this one, 200, this one, 300, this one, 400, this one. And you see that in one-by-one calculation, the convergence speed decrease when the number of grid increase. While if we use direct calculation, you see that this is almost independent from number of grid, and we have the same convergence when number of grid is 100, 200, 300, and 400. So let's go to the MATLAB and just implement this matrix form calculation. Okay, this is the same code that we have derived in the previous video, and I just explained line by line. And there was a mistake in the previous video about the units. The units for potential, that is V, here should be volt, not volt per centimeter. Just you can correct it here. And this is the term that we have derived for nonlinear Poisson equation, and this line represents the same formula that we have tried for the linearized Poisson equation. Now all we want is to implementing of the matrix form of the equation that we derived here. Okay, what I did here, just enter, and I want to disable all this term with Control R. Therefore, what we need to first create matrix M, right? Matrix M. Therefore, here I start with some loop 4. I need to change I from 1 to from 2 until n minus 1, right? And m I equal, it should be equal to, if you notice here, what do we have for m? This is m11, m22, 33, and 44. You see that we have h squared, right? We have for mii should be a multiple to the h squared, multiple to the h squared, multiple to the what? Multiple to the ni plus 1. N plus 1 divided by the thermal minus 2. Okay, same term. Why plus 1? Because you see that this is m22. When we substitute I to be equal to 2, we have n3. Therefore, this one should be I plus 1. Okay, just before that, what we need, you see that this orange line under m, because we need to allocate some memory for m, and I here defined m to be zeros, n minus 2, n minus 2. Why n minus 2? Because you saw that I derived the system of equation by assuming that the number of grids is 6, right? And what we got for the matrix M, dimension of matrix M is 4 by 4. It means that when the number of grids is n, the dimension of matrix should be n minus 2 by n minus 2. And why? Because we just excluded the elements that represent the boundary conditions V1 and V2. Okay. Then what about m I minus 1 and I? If we substitute I be equal to, what we have? We have 1, 2. What is 1, 2? The element 1, 2 is this one, and that one is equal to 1. And another term, I minus 1, right? If we substitute I with 2, we have m21, right? And what is m21? If you notice, this term is m21, right? Therefore, we have created m21 also. But if you notice, by changing of I from 2 until n minus 1, we can create all the term, right? We can create all the term, and sorry, this one should be n minus 2, not n minus 1. For example, when n is 6, it will be 4, and if you substitute 4 instead of I, you will create this term, right? Okay. We will create in this term, and this term. But we have not created this term. Why? Because I started I with 2. Therefore, what I need, I just define I here to be 1. When I is 1, I have the same term here. Just Control C and Control V. And by substituting I equal to 1, we have M11. Why I excluded I equal to 1? Because if I started with 1 here, we will have 0, 1, and 0, 1 is not defined in the MATLAB. Therefore, because this the number inside the parentheses shows the index or shows the position of the number in the matrix M, and the position of number cannot be 0. This is just start with 1 1 1 2 1 3 2 1 2 3, so on and so forth. That's why I just wrote the M11 out of this loop. Okay, so we have the matrix M, we created the matrix R. Now what we need to create the right hand side matrix. And what is the right hand side matrix? The right hand side matrix is RHS, and that one is AH squared, A multiple to the H squared multiple to the V old, right? Yes, V old divided by V thermal divided by V thermal multiple to the N yes, multiple to the N plus AH squared plus A multiple to the H squared. What else? Multiple to the N1 multiple to the N1 minus again Ni. And we need to put a dot here, because putting dot means that we have two matrices here, V old and N. They both are matrix, and if we do not put a dot here, it means that the multiplication is a matrix form multiplication, while putting a dot means that each array multiplied to its corresponding array in the matrix M. Okay, just a semicolon here, and we need to create right hand side capital B, and that one is what? I think we can create this right hand side B out of the loop here. Right hand side B, let's first allocate some memory, and it should be zeros and minus 2. Well, we have only a column for the right hand side B, and we know that all the term in the right hand side B is 0 except then the first term, right hand side B 1 indeed is V1 and V1 is V left. We have defined here. We know the value of the potential at the left and right boundary, and the last element in right hand side B, just put an end here, it is equal to the V right. What we defined the zeros for right hand side B, and we just assigned V1 and V6 to the first and the last term. What else? And therefore, by having out the right hand side and right hand side B, let me define the whole of right hand side with capital RHS, right hand side, and that one is right hand side minus to the right hand side capital B. What else? VC will be equal to what? Inverse of matrix M multiple to the right hand side, and you can do this with the following command: matrix M backslash capital right hand side. This backslash means that the inverse of matrix M multiple to the right hand side of the matrix. And one more thing before continuing, if you notice to the slides, what we have in the right hand side is, you see we have N2, N3, N4, N5, and we all 2, 3, 4, 5. We do not have N1 or N6 or V old 1 and V old 6. Therefore, we need to define a new array for N and V. Let's call them with NC and V old C. And this one here should not be zeros. Okay, therefore just I copy this one, Control C and Control V, and I define N underline C with some zeros minus 2 and 1. Also we underline alt underline C again with zeros and 2 minus 1 and 1. Control C, Control V. And here I need to, here or here, no matter, let's put it here. I need to define another loop for I from something to something, and I need to assign V underline alt underline C. I should be V underline alt I plus 1. It means that when I should change from 1 until n minus 1. It means that when I is 1, we give V2, V alt 2 to V alt C1. Yes, correct. And same for NC, right? It means that n underline C I should be n I plus 1. I plus 1. Again, when I is 1, here is n2, we give n2 to nc1, and we created just V alt center and n center. Therefore, here it should not be V alt, it should be V alt center, and it should not be n, should be nc, and we define nc and V alt here. And here should not be I. We are using matrix form n1 minus n. What else? Another thing, here we calculated VC, but here in defining of error, we subtract V alt from V. Therefore, we updated VC and we need to update V. Therefore, we need to define another for I should change from something to something, and now we need to give this VCI. Let me think. This VC. Okay, let's say VI, and this V underline C. If I changed from 1 until n minus 2, it should be 2. Yeah, it should be 2, and it should be I minus 1. And I should change from 2 until n minus 2, right? And we give VC I minus 1 to I. When I is 2, it gives V1 to V2. And when n is minus 2, here is n minus 2 minus 1. It will be n minus 1. We give n minus 1 to n minus 2 V n minus 1. And semicolon here. I think now everything is okay. We have defined matrix M, right? We defined right hand side. We defined right hand side B here. We defined, we calculated VC, that is inverse of matrix M, multiple to the right hand side. And we updated V by having the central V, and everything is the same. Just let's press F5 and see if everything is okay. There's no error. Okay, change folder. There is some error. Let's check. Zeros in line 28. This one should be zeros, and this also should be zeros. This one also should be zeros. F5. Another error, matrix dimension must agree, and this n, yeah, this n also should be NC, central matrix for n. F5, matrix dimension must agree. Right hand side B. What is the right hand side B dimension? Right hand side B dimension n minus 2 and 1. But what if right hand side? Just let's look at the dimension of the matrix here in variable. we need to right hand side, and this is 99 by 1. But this right hand side should not be 99 by 1, it should be 98 by 1. And what about the right hand side? Right hand side B. Right hand side B. Dimension of right hand side B is correct, 98 by 1, but this right hand side should be 98 by 1. So why does it 99 by 1? It comes from either VOC or NC. Let me check the dimensionality of this matrix NC, and NC is 99. Should not be like that. What about VOC? Where is VOC here? The dimensionality of VOC, here. I think this one should be n-2. Let's check it again. Now everything works, and you see this is the convergence, and this is the appearance of the potential, but seems that something is not correct again, because we know the solution format. We can check it here. I just enable it with Control T and disable the new added terms with Control R, press F5 again. We know that the solution should be like this, so something is not true here, and let me find why the solution is not correct. Okay, just one more time, press F5. You see that the convergence is okay, but there is a problem here. I think problem is in V. I think problem is here, because when we update V from VC, this one should be n-1, and when this is n-1, this is n-2, we give n-2 to n-1. Yeah, I think when we change this 1 to 2, it should be works. And this is the convergence, and yes, you see that. Yes, you see we have the same solution that we have with the one-by-one calculation. And I want just to compare the convergence. Let me just close this figure and this figure and disable this one, Control R. What else? I want to compare only error, Control R. I need to add and hold on here. Now, okay, let it be with red. Now this, pressing F5, this is the convergence for direct calculation. Now this time, okay, disable all this term, Control R, Control T, and this time let it be with blue, and it should Control Z, Control R, it should shows the convergence for one-by-one calculation. And here, yes, you see the blue one shows for one-by-one calculation, and the red one shows for direct calculation when n1 is 1e14. You see, for 1e14 we have a considerable increasing in the convergence speed, but when n, let me close this one. Okay, but when n is 1e17, okay, now blue one is for direct calculation, press F5. This blue one for one-by-one calculation. Now disable one-by-one calculation, enable allow these commands for direct calculation with Control T, and I'm changing blue with red, press F5, and you see again the red shows for direct calculation, blue for 1 by 1 calculation. When n1 is 1 is 17, and you see that again we have enhancement in the speed of the convergence. This is the same graph that I showed you in the slides. You see this one is the same graph, blue or 1 by 1, and this is for direct calculation. And you can also derive this graph by yourself and check for different number of grids for 1 by 1 calculation or direct calculation. Okay, what else? You remember that in the previous video I said that we need to have some initial guess, and I assume this initial guess to be 0 everywhere except in the boundaries that we know the value of the potential at the boundary. Now I want to show you the effect of the initial guess on this two method, 1 by 1 calculation and direct calculation. Let's assume that potential instead of being 0 is what? Let's assume that this is linearly changed between left and right boundary condition. Therefore, V is V left, right? V left plus V right minus V left multiple to the x divided by d. It means that when x is 0, potential is V left, and when x is d, potential this will be 1, this cancel, and potential b will be V right. Okay, now what I did, I just used this potential linearly change between left and right boundary condition to be as the initial guess. Let me save it somewhere. For example, V in that represent V initial. I save this V here to plot it later. Let's plot here. Let's plot that here. Control T, Control T, Control R. I want to plot Control C, grid on, hold on, Control V. I want to plot with initial V initial with some dashed blue line. Let's just check. I think okay, I need to change this one to 1E14 and enable this closal. Control T, press F5. Okay, this is the convergence. Just let me enable this tolerance line. Control T again, F5. This is the convergence, and this is the initial guess indeed. Let me check the color with some red. F5. Okay, this convergence. This is indeed our initial guess. We assume that the potential change linearly between left and right boundary condition, and this is the final solution when number of grid is 1E14. You see 1E14, and this is for direct calculation indeed, right? Just I want to check it for also for 1 by 1 calculation. Control T, I disabled all commands corresponds to the direct calculation with Control R. Okay, again F5. This is the convergence, true, and this is the final solution, and this one shows the initial guess. And you see that we have convergence, and the potential format is correct. The final solution format is completely true. This is for 1E14. Let me change this the N1 from 1E14 to 1E, for example, 17, right? Press F5. Again, we have converging of the problem, and this is the format of the potential, and this is the initial guess. Just let me increase it to 1000 to have accurate value for the potential at the boundary. You see that with this new initial guess, with this one, we have convergence for all value of the N1. But what if I try this I try this new guess for direct calculation. I disable this one-by-one calculation with Control R and enable all of the command for direct calculation with Control T. I'm changing from 1E17 to 1E14 and press F5. We have the converging of the problem. Yeah, this is the initial guess, this is potential. Let's increase N1 from 1E14 to 1E15. F5. We have again convergence, and this is the potential for 1E16 for N1. F5. You see, we have although a convergence finally, but seems that the solution is let's not say solution, the convergence is very fragile, right? You see that there is a fluctuation, but it's finally converged at somewhere, but the number of iteration is more than 100. And I think if I increase the N1, it won't converge anymore. Let's increase it with 2E16. It's already converged and the solution is correct. Okay. 3. Still converge. What about 5? You see, there is no convergence graph because not a number is appeared for error and for potential. If I just open the potential, V. Okay, where is V? You see that not a number is appeared for the V. And you know why? Because the disadvantage of this direct calculation is that this is really sensitive to the initial guess. If I disable this initial guess that I defined later with Control R and press F5, see we have true solution. We have true solution with such an initial guess. This is the final solution, this is the initial guess. Just increasing number of grids to have more accurate potential. So see the convergence is okay and the solution is okay with such initial guess. But what if I use this initial guess, Control T? See, we do not have converge and not a number appeared for the potential. It means that we have diverging initially, and I can show here easily by this command. Instead of having large number of iteration, let's just look the iteration when looks for 3 iteration, for example, and for 1 iteration. You see that this is the format of the potential for 1 iteration and for 2 iteration. And the not a number appeared here. Sorry, not a number appeared here. Control R, Control T. So as a conclusion, we saw that by direct calculation of the potential instead of one-by-one calculation, although we can have increasing of the convergence, we can increase the speed of convergence, but such a calculation is very sensitive to the initial guess. And when the initial guess is really far from, when the initial guess is far from the final solution, you saw that the problem converges very fairly. But for the one-by-one calculation, the converging of the problem does not relate to the initial guess. If you notice here, just I don't know what's happened. There's another MATLAB here. Just let me close this one. Okay, one more time. When N1 is 1E16, press F5. This is busy. Why? Just Control C. Okay. Let me decrease this one to V1, E4, F5. to still calculate. Let me, okay, Control C. 1E3. I just restricted number, maximum number 1000. Okay, but because number of grid is very high, I just reduced the number of grid from 1000 to 100. Press F5. Okay, and you see that when number of N1 is 1E17, Control T, we do not have any converging of the problem for such initial guess. While using of the direct one-by-one calculation, we can have the converging of the problem. Control R, okay, and F5. You see that we have the converging of the problem for one-by-one calculation, and no matter what is the initial guess. Why? For in using of the direct calculation, the problem is that when the initial guess is really far from the final solution, the convergence is not guaranteed to be achievable. I think that's it for today. Thank you for your attention.